All right, so in this video, we're going to talk about infinite sequences. And up on the screen, I've defined how we're going to view our sequences. We're going to say a sequence is a function whose domain is the set of positive integers. So the allowable values to input for these sequences will be things like 1, 2, 3, etc., etc. So positive integers. The notation that we're going to use, instead of y equals f of x, like you might think of it for a function, now that we're dealing with sequences, we're going to use a sub n equals f of n. Okay, so as we look at this stuff, a lot of similarities will be found between the sequences that we're dealing with now and the functions that we've dealt with in the past. Now, if we view these informally as a function, we should always think about the graph. So let's take a look at an example here. And the notation that I'm going to use in this example is pretty consistent throughout most textbooks, where we have the actual sequence itself, and in this case, n squared, acting as our function, in set brackets. And then many times you'll see things like n equals 1 to positive infinity. This tells us which number, which positive integer to start with. If there's a domain restriction, this might be different, but in this case, we're perfectly fine starting at n equals 1, going up to positive infinity. Now, when you look at a graph of this, remember this is now going to be your n-axis, and this will be the a sub n, or the output. And we would start with our 1, and if you plug in 1 for n, it's going to spit out a 1. So that's going to be our 0.11. Then we could continue by plugging in a 2, and you would see that maps up to 4. 3 would then map up to 9, etc., etc. Now, what's happening is you're essentially plotting points as you would a function. Well, we all know this is a parabola that opens up, and if we were, in fact, graphing y equals x squared, your parabola would look something like this. This is considered a continuous function where every single value maps to another y value, and so that's where you get this filled in graph. Over here, because we're only using positive integers, you're going to have these spaces through here. Now this graph will continue, of course, to increase all the way up, and you'll be able to see that parabolic shape, but you will in fact only have these points. Okay, so the fact that these graphs look the same is great, but they're not. These will have a countable amount of points through it, a discrete function, if you will, and this would be our continuous function. All right, so let me go ahead and put another real quick example up here on the screen, and I will talk about how these compare. So now if we look at something like n over n plus 2, when n ranges from 1 to positive infinity, you'll start to see if we plot a bunch of points here, which I'm not going to do in the video, but if you plot a bunch of points, you're going to see this thing start to look like this. And one of the key differences between the example I have here versus the example I have here is the fact that this one will end up continuing to increase and go to infinity, while this one actually limits. So as we talked about a moment ago, anytime we have a function, we think about a graph. Anytime we think about a graph, we think about limits. This example right here would actually go off to infinity, so we say that it diverges. However, this other one will limit. We say that it converges. And in this case, it's going to converge to 1. I know that because I have a horizontal asymptote here at 1. And to come up with that, to think about where that comes from, again, if we view this as a function and we take the limit as n goes to positive infinity, you would have that horizontal asymptote at 1, therefore limiting our graph from going any higher, therefore converging. So it's kind of a trickle-down effect. When we think about sequences as functions, we can view them graphically. If we view them graphically, then we can go ahead and think about them limiting in terms of converging or diverging. So I'm going to go ahead and clear the screen. We'll get a formal definition up, and then we'll take a look at some examples. Okay, so let's take a look at the definition here of a sequence converging. So just kind of ignore the picture for a minute here, and we'll say that a sequence A sub n converges to limit L if given epsilon bigger than 0, there exists a capital N such that the distance between A sub n and L is less than epsilon for all lowercase n bigger equal capital N. Now, the definition itself is a little bit hard to follow, but I think I can talk you through with this picture above. In short, what we're saying is that the limit as n goes to positive infinity of A sub n is going to equal L in the case that it converges. Okay, so let's think about this. We've got our sequence A sub n. We're going to have a bunch of points, right? Just the points. And that's what you're seeing up here, just the points. We're going to have this sequence converging to limit L, which here's our limit L. You can kind of see it starts off and it bounces around and then all of a sudden starts to come in limit close to this L. If given epsilon bigger than 0, remember epsilon is just a really small positive number. All right, so you can see we have L plus epsilon and we have L minus epsilon. There exists a capital N, so there exists this value. So it's going to converge if this value exists. And in this case, you can see it's approximately 13, not that that matters in this example, but assuming this N exists and assuming beyond it, all of these other points are going to be within the L plus epsilon and the L minus epsilon. So that's where the distance comes into play. If the distance between the points and L are less than epsilon, that means it's going to fall between these two lines, then we can say that it converges. Okay, and that's true for any sequence that we're going to talk about. If there's some value in right here that exists, meaning that all of these other points are going to be within these two dashed lines, then we're going to be able to say that it converges. If it doesn't converge, if this guy doesn't exist and somewhere down the road there's going to be a point outside this space, then we would say that it diverges. So if not convergent, then it diverges. And there are a variety of interactive sites online that you can go to that'll allow you to play around with this and move in around and deal with different sequences. So I would encourage you to do that to get some better clarification if necessary.